we were discussing about this second order system and how a second order system can be how a third order system can be approximated into a second order system. So let's take up an example of this. Look at the system here. It is 1 divided by s plus 2 into s plus 4 into s plus 6. So what is the order of the system? What is the order of the system?
Third order system, sir.
Third order system. Okay. So how do you convert this into a second order system? What do you do for converting this into a second order system?
You have to multiply with the gain, sir.
Okay. So which pole are you going to eliminate?
S plus 6, sir. Minus 6 is the pole we can eliminate.
Okay. So you eliminate the minus 6 1. Okay.
So we eliminate the
Yeah. Okay. So this can be written as k divided by s plus 2 into s plus 4. Okay. So this is k divided by s plus 2 into s plus 4. Now what should be the value of k such that zeta is equal to 0.5? Okay, what should be the value of k such that zeta equal to 0.5? So how do you do this? So how do you do this? Zeta equal to 0.5 when it is given.
So we put S equal to 0 and then we find K, sir. We equate the equations, both the.
Okay, but there is a requirement given here. Zeta is equal to 0.5. Okay, so there is an extra requirement given, zeta equal to 0.5. So what you do is, this is a closed loop system. Okay, so this is a closed loop system. So you find the transfer function for this. So we were just taking y of s by r of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Okay, but this is not in this form now still. So we need to bring it to this form, y of s by r of s in this form. So how do you bring that? So you have this gc of s into g of s is equal to k divided by s plus 2 into s plus 4. Okay, so you're leaving out this s plus 6 here, so you need a k. Okay, so for this you take the closed loop transfer function. So what do you get? So what is the closed loop transfer function of this? K divided by, this is s square plus 2s plus 4s, this is 6s plus 8 divided by 1 plus k divided by s square plus 6s plus 8. What will be this? You take s square plus 6s plus 8. This will be s square plus 6s plus 8 plus k. Okay, so this thing and this thing gets cancelled. It will be k divided by s square plus 6s plus 8 plus k plus k. So when a system like this is given, okay, you have to find the transfer function of this type. Okay, you can't just take only this and do it, because this is a closed loop system which is given here. This is closed loop. Okay, so because of that you have to find the closed loop transfer function, k divided by s square plus 6s plus 8 plus k. Now this is written as omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now if you compare these things, 2 zeta omega n is equal to what? 6. Okay, s term. Then omega n square is equal to, sorry, omega n square is equal to 8 plus k. Is it fine? So what is given here? The given value is such that zeta equal to 0.5. Okay, so you substitute zeta equal to 0.5. How much do you get omega n equal to? What is omega n from this equation?
6, sir.
6.
Yes, sir.
Okay, what is k? What is k?
28, sir.
K is 28. Okay, so what does this mean is, so this was the system which was given, 1 divided by s plus 2 into s plus 4 into s plus 6. Assuming a second order approximation, okay, he has given to assume it to be a second order system approximation. So you write it like this, k divided by s plus 2 into s plus 4. Okay, design a gain adjustment controller, C of s is equal to k, such that the damping ratio zeta equal to 0.5. Okay, so this is the requirement. So damping ratio must be equal to 0.5. So what will be the value of k? So you just can't do it for the open loop transfer function. You have to do it for the closed loop transfer function, because this is what is given. Okay, so this is for the closed loop transfer function. Now what you did was you took the closed loop transfer function and then equated that to the second order system characteristic equation, and then with the given data omega and zeta equal to 0.5, you found out what is omega and what is k. Okay, so if you put k equal to 28, then the damping ratio should be equal to 0.5. Okay, so this is what we understood. Now let's try doing this in MATLAB. Okay, so I'll just so this is a second order. Okay, second order. So it is 1 divided by, so this is s plus 2, okay, multiplied by what? and divided by s plus 2 into s plus 4. So s plus 4. Now what you want to do is you want a control system designer. Okay. So get this. So this opens, close this one body and expand this thing. Now there's a design requirement. Okay, so if you right click here and say design requirement new,
So your
Sir,
MATLAB window
are
isn't
you?
seen.
We can't see
okay,
MATLAB
okay,
screen, sir.
okay, just a second. I didn't share the screen. Okay, so MATLAB, what I did was now we are able to see.
Yes, sir.
Yes, sir.
So 1 divided by s plus 2 into s plus 4 I have given. Okay. And then open the control system designer. So you have 2 poles. Okay. Have 2 poles. So there is a design requirement to be given. If you right click this and say design requirement new, what you get here is the rise time, settling time, percentage overshoot, and all those. This we don't want. So right click over the root locus editor, okay, and then say design requirement new. Okay, here the design requirement type is damping ratio should be 0.5. Okay, so this is what is given. Now you get this. So move this thing. Okay, move this till this black line. Okay. Okay, and then right click and say edit compensator. What was the value you got? K? Which you got K?
8,
Eight,
sir.
28, sir. 28, I think.
28.
28.
28, okay. So is that little more is required. We have damping, you can see it is now 0.5. Okay, so it compensate 27.77 something. Okay, so if I click here on the bottom of the screen, I don't know if you are able to see. On the bottom of the screen, you can see the. Just a second. So you can see here this thing damping. Okay, 0.505 it is. Okay, take it as 0.5. And natural frequency, how much we got? 6. Okay. So that is the natural frequency 5.95, and take it as 6, and then you go to edit compensator, you get the K value. Okay, so what you're doing is, the first thing what you did, the calculation was, you took the K, you found out what is K by hand calculation. Okay, so you were trying to do by hand calculation what is the value of K when zeta equal to 0.5. So that is what you did. But when you use MATLAB, you can directly get the value of K when you put a design requirement saying, the damping ratio must be equal to 0.5. Okay, so this is the border. If you cross this border, then the damping ratio is going to reduce. Okay, so see here, 0.46. Okay, so on this line it is 0.5. On this line, if you are there, it will be 0.5. Okay, I'm not exactly positioning, so that's the reason. Okay, any questions in this? Any questions?
No, sir, no questions.
Did you are you able to understand this? Why you took the closed loop transfer function here? Because this was a closed loop system. Okay. Previously, what we did, we just took a second order system of this type, and then we said we need to have this K thing. Okay. So only this was given, but now this has a closed loop system. Okay. So you need to have a transfer function of this format. So what you do, you take the closed loop transfer function and then substitute the given data, find out omega and find out K, and that solves the first question. Design a gain adjustment controller. C of S is equal to K such that damping ratio zeta equal to 0.5. So if K is equal to 28, then zeta will be equal to 0.5. So any questions on this? Any questions? Okay. So,
No,
okay. Can you try this one? What you need to do is forget the ramp input, do it for a step input. Okay. Find the zeta. Find the zeta. So how do you find zeta? Let's do it by MATLAB first. Okay. 4 divided by s into s plus 2. Remember, um, when you do the calculations, you take the closed loop transfer function. Okay. But when you give it in the MATLAB for the control system designer, you just give the open loop thing. Okay. So that will convert into a closed loop and then give you the result like this. Okay. So, but when you are doing it, you have to take the closed loop transfer function and then solve it. Now, we had one question. So 4 divided by s into s plus 2. Okay, we'll try this. Just close this one. 4 divided by s into s plus 2. Now what do you get? Okay. So what is the question? Question is put k equal to 1. Okay. You should put k equal to 1. Find zeta. Okay. Find zeta. So how do you find zeta from this? What is zeta here? Can you see? Can you read the value zeta?
No, sir. I can't. If there's no zeta value shown.
No, sir.
It's there, sir, at the bottom, 0.5.
Yeah, bottom line. If you see,
Sir, bottom right, it is 0.5.
yeah,
And
damping.
omega n is 2 radians per second.
Yeah, damping is 0.5. Natural frequency is 2 radians per second. What is the k value? K value is 1.
Yeah.
Okay. Damping is 0.5 here. Natural frequency is 2 and k is 1. Okay. Can you get this by hand calculations? Can you try doing this by hand calculation? The same thing. So how do you proceed? If you have to do it by hand calculation, it will be what? Tell me. How do you do the same thing by hand calculation? Yes, someone.
So we find GC of S into G of S, and then we compare that with the closed loop transfer
GC
function.
of S into G of S is what? GC of S is
1.
equal to 1. Okay. 1 into G of S is what? 4 divided by S into S plus 2, which is nothing but the same thing. 4 divided by S into S plus 2. Then what you do?
Sir, it will be, we should write 4 divided by S square plus 2S divided by 1 plus.
You have to take the
You
closed.
have to take closed
Closed
loop
loop
transfer function, sir.
Okay, 4 divided by S square plus 2S, okay, divided by 1 plus 4 divided by S square plus 2S. Okay, so this will be S square plus 2S. So this will be what?
It will be 4 divided by S square plus 2S plus 4, sir, total answer.
The answer will be 4 divided by S square plus
2S plus 4.
2S plus 4. So what is omega n from this?
Omega n is 2, sir.
2. Okay, this is omega n square. Okay, so if 2 zeta omega n is equal to 2. Okay, omega n is 2. 4 zeta is equal to 2. Zeta is equal to
0.5.
that is what you got in MATLAB, no?
Yes, sir.
Okay, so the same thing we have done the calculations, and that is what we see even in the MATLAB 0.5 and 2. Okay, so what is this current location? What do you mean by current location? Yes, can somebody answer that? What do you mean by current location?
Location of the pole, sir.
Yeah, see here the problem. What was the position of the pole? It was one was at where are the pole positions? 0 and -2, correct?
-2.
Yes, sir.
Here S is equal to 0 and S is equal to -2. Okay, so these are the two pole positions. what pole positions are there? Open loop. Okay, the pole positions are open loop pole positions. Okay, now when you make it as a closed loop, the pole positions will change. Okay, to what it will change? It, see, first it was s square plus 2s is equal to 0. Okay, so you had s is equal to 0 and s is equal to minus 2, but now it is s square plus 2s plus 4 equal to 0. Okay, so what are the pole positions for this? S square plus 2s plus 4 equal to 0. You find the roots for this. Okay, you find the roots for s square plus 2s plus 4. Can somebody find out and tell me? Use the calculator, solve this quadratic equation s square plus 2s plus 4 and get the closed loop pole positions.
One is minus 1 plus root 3i. Another is minus 1 minus root 3.
Minus 1?
Minus 1 minus root 3i, sir.
Root 3 is what?
1.73. Yes, sir, it's coming same.
Yeah, that is what you see here. Okay, minus 1 plus 1.73i. Okay, this one, and this one is minus 1 minus 1 point. I'm not clicking it properly. I'm not changing. Shouldn't be changing it. Okay, so I will go edit the compensator. I'll make it as 1. It will go correctly to those positions. So this is minus 1 minus 1.73i. Okay, so what position is this? Closed loop pole positions. Okay, these are closed loop pole positions for the gain equal to 1. Okay, do you understand this?
Sir.
Okay.
Yes.
So it says also find the steady state error to a step ramp input you leave and the settling time. So you can go to the MATLAB, right click here, say characteristics, settling time. So settling time is this one. Okay, 4 point something, 4.04 is the settling time. Okay, and then steady state error. Characteristic steady state. Okay, if you click here, it is 1. Okay, final value is 1, so steady state error is 0 only. Okay, so this is how you understand and do these things. Okay, you find the closed loop transfer function and then equate this with the kind of system here. Okay, second order system, and then get the omega n and zeta and all these things. So you must be able to understand what MATLAB is showing you. Okay, so if you see here, these are nothing but the closed loop pole locations. The magenta color, that is closed loop pole locations for the gain equal to 1. Okay, if you want to find the gain, right click here, click on edit compensator, you can find what is the gain value. If you change the gain value, what will happen? The pole positions will again change. Okay, say if I make it 10, then the pole positions are going to change. Okay, So if I click here, the pole positions have changed now. Okay, damping ratio has changed. So what we did was we did not want to edit here. Okay, we did not want to edit the compensator, but we gave a design requirement. Design requirement. Oh, okay, not for this one. For the other problem, we gave the design requirement for zeta equal to 0.5. For the first problem, we gave the design requirement. For the second problem, we found out what is zeta. Okay, found out what is zeta. So how do you give a design requirement? Is just go to MATLAB and say, if you are giving a design requirement in the root locus editor, okay, right click, you can say new. Okay, here you can give the design requirement type. You have the natural frequency also, you have the damping ratio, you have the percentage overshoot, you have the settling time. So all these can be defined here. If you say you want a design requirement of damping ratio, say 0.6. Okay, so if you move this poles over here, then the damping ratio at this border, this black line, will be 0.6. Okay, so have you seen this damping ratio lines like this previously? Previously, have you seen
No,
this?
sir, we have not seen. This is the first time we are seeing.
This is the first time you're seeing. Have you seen the pole zero map with grid on?
I don't think so.
Pole zero map with grid on, I had shown you the damping ratios. Okay. I don't know if you remember. So if you, instead of the control system designer, you just have the PZ map, okay, with the grid on, you can see the damping ratio constant lines, okay. So that is what it is. So this is one line which is indicating that this line is indicating the damping ratio is 0.5, okay. So within this, it will be increasing, okay, because here what you define, when you define this design requirements edit, it says damping ratio greater than, okay, damping ratio greater than 0.6, okay. So this white regions are okay because you want the damping ratio should be greater than 0.6. But if you want it equal to 0.6, then it must be on that line. On that line, you get damping ratio as 0.6 because that is what you have defined here. Okay. So once you have the damping ratio condition, then you can right click and find out what should be the gain value for getting the damping ratio of 0.6, what should be the gain value. So this is how you find out. Okay, so these things can be done either by hand calculation or can be done by MATLAB as well. So both I have shown you. So you just try these things, try it out by hand calculation, try it out by MATLAB as well. Okay, so basically what you're doing here is you're designing a controller, okay, for a approximated second order system such that the damping ratio is 0.5. Okay, so that is the first problem which we saw. Okay, so these are some things which you can try both by hand calculations as well as the MATLAB. So for the test or exam, if it's a written test, then you will be asked to do these things, do these hand calculations. Okay. If it's a lab, control lab, then you'll be asked to directly find the gain value using the control system designer app. Okay. So those who are working on mobiles, we can do the hand calculations also. Okay, so we'll see when it comes to the test and exam for the lab, we'll see how to go about. But try doing these things, try doing these, and then yeah, you can always verify your calculations with the MATLAB result. Okay, so try giving some design requirement here in the root locus editor. So if you have already given, you can go and edit it. If you're giving it new, you can click on new and give the different things what is given in the problem. If there are two things given, you can define two things. Okay, so you can look at the problem and define that and then find out the rest of the things from that. So this is how you solve these problems in the control engineering. Any questions? So the reason for starting with the second order system is you are familiar with the damping ratio and the natural frequency. Okay, that's the reason I started with the second order system. Otherwise, as per the syllabus, it is first order and then second order. First order you have not been in touch with. Okay, you have studied vibrations, so I've started with second order systems. Okay, so second order systems are easy to understand because you already know zeta and omega, but first order systems would be a little different. So after this, we will start with the first order system. Any questions? We just did two numericals today. One was this one and another one was this one, where k was given, find zeta. Here zeta is given, find k. Okay, just the reverse of the two problems. Here in the first one, you eliminated this s plus 6. Okay, given the third order, so you removed this s plus 6. But here it was already a second order only. Any questions?
No, sir.
No, sir.
Even so today B section has a lab. So 11:30, please log in and ask any doubts if you have. Let's use that lab time for clarification of the doubts. Okay then. Thank you.
Thank you, sir.
Bye.